This is the 7th installment of Philosophy 201 Introductory Logic. Today, our topic is the rule of inference called or elimination, also known sometimes as proof by cases. In one sense, this is the most complicated rule actually in one sense, of the entire semester. However, it's only complicated in the details. So it's a very complicated rule to carry out all the details correctly. The concept behind the rule is actually quite simple. So as I said, the other name for this rule is proof by cases. It's a kind of argument we often give in life where we know that one of several possibilities holds, but we don't know necessarily which one of those possibilities holds. And then we argue case by case, and we say that one thing follows, one and the same thing would follow in any case. So it's a proof by cases, arguing through the cases. So here's an example of the kind of thing I'm talking about, put in abstract form. So to put this a little bit jokingly, of course, we have an expression in English, the expression, damned if you do, damned if you don't. Now, the idea behind that expression is you may have two possibilities in front of you. If you do the one, you're damned, things will go badly for you. If you do the other, you're damned, things will go badly for you. So it actually doesn't matter which possibility you choose. Now, putting that kind of thing in abstract format, suppose the two possibilities are P on the one hand and Q on the other hand. Now, suppose that in both cases, you know that if P, then R. You also know that if Q, then R. Now, we all know intuitively, suppose now we have these three things hold, looking at the slide here, if P then R, if Q then R, and also we know that either P or Q. Intuitively, we know that R is the case. But once again, with logic, we want to argue that that's the case. So how would we do that? And here the idea behind the or elimination rule is we use the same kind of strategy we used for conditional proof. That is, we make a supposition. So we don't know whether P is the case or Q is the case. We know that one of the two is the case. So we say, suppose that P, and then we proceed to argue. So I'll write that like this. Suppose P, and then let's argue. So under the supposition of P, well, we know if P then R. So now I'll start to make this look a little bit more like a proof. So we know that if P then R, so since we've supposed that P, we get R. Okay, now on the other hand, if we suppose that Q, so the other supposition, suppose Q, again, now by line 2, we have also that R. So using 2 and then the supposition of Q, we can use modus ponens to get R. Now, conditional proof. So at this stage, we've just gone through, granted that you can suppose P and suppose Q, which of course, by the rule of assumptions you can do, you can get R in either case. But now the rule of or elimination tells you, if you can do that, then you may do the following. You may now infer R on a line by itself. And that's going to be an or elimination. It's going to be an or elimination from, and this is going to be the hard part of, so the idea here was clear. The idea was you have a disjunction, you argue case by case. Now, how do we tabulate everything in the right way? So we'll have here at our final line R, that will be or elimination. Actually, let me write that a little bit further to the side. We're going to have to name all the numbers that were involved here. So it's going to be or elimination. Now, the numbers we're going to name are, first of all, the disjunction. So in this case, our disjunction here occurs on line 3. So it's going to be line 3. That's our disjunction. Then actually what we're going to do is we're going to name the first supposition. So here, I'm going to change this where I wrote suppose P. I'm going to change that into a proper line of a proof. So suppose P becomes for a new assumption. Now, this is not linear as a normal proof, so I've written this off to the side, but now this becomes P on the right. I'm gonna add this number in just a minute. Let's continue down on this left-hand side. So there's the supposition of P. Now from 1 and 4, we get R by modus ponens. So this is a supposition, line 4, then 1, 4, modus ponens. As usual, we collect the numbers. So 1, 4 on line 5 gives us R. Okay, now let's repeat on the right-hand side. Okay, so I'll start back now at line 6. Line 6, that's a supposition now of Q. And now line 7, again drawing the conclusion R. Now this is modus ponens from 6 and 2. Okay, so now pause for a second. Notice it might seem strange. We have R in 2 places now. R occurs on line 5, R occurs on line 7. They're playing very different roles there. The R on line 5 is something we derived from the assumption of P. The R on line 7 is something we derived from the assumption of Q. As you can see, they're dependency numbers, right? The R on the left, number 5, R in number 5 depends on 1. The R on the right depends on 2. Actually 2 and 6, of course. And so these are different. Now, the rule of OR elimination is going to tell us line 8, that's the next line in the proof, R follows from 3, that's the disjunction. Then it's going to follow from, I'm going to use a blue color here so we can see what's going on clearly. Here, over here is the first conditional proof. It's not the rule of conditional proof, but a supposition of P, derivation of R. So we're going to name those 2 numbers. So 4, 5, 4, 5. Then over here, the second subproof, line 6 and 7. Okay, so as I said, OR elimination is complicated. You have to name 5 lines to do OR elimination. You name the line of the disjunction. You name the 2 lines that correspond to the first subproof, an assumption and a derivation of the conclusion. Then the second subproof, the green one here, the assumption, the supposition, and then the derivation of the second instance of the conclusion. That's the 5 lines that justify OR elimination. Now, finally, let's tabulate dependency numbers. This will take many practices with OR elimination to become fluent using these dependency numbers. Basically, what you do is you carry down all of the dependency numbers that are beside the disjunction. In this case, it's just 3. So the disjunction is 3. So we have that. Then we take the dependencies of the end of the first subproof here. So going back to my black color to not get things too confused, we carry these down. However, we delete the supposition, which is 4 in this case. So that gives us just 1. And then over here on the right, we carry these down, but delete its supposition, which is 6, gives us just 2. So then our dependencies are 1, 2, and 3, which is what we hoped for, because if you look back at lines 1, 2, 3, R should follow from those, and that's what we have now on line 8. Okay, one last thing I'll do here is now I'll just stack these on top of each other so you can see, of course, this is just a linear proof. I push these out, the 2 subproofs out to the sides to make it more clear what's going on, but let's just go back now and tidy this up. So we'll erase these extraneous marks. Okay, and then finally, we'll take this subproof on the right and move it down into line. We'll take this subproof on the left, move it back into line, and just clean it up a little bit. Okay, so now it's starting to look something like a real proof. Okay, so that's roughly speaking what the final proof looks like. The line numbers have gotten a little bit messed up. Let's just go back. That's an assumption on line 6. Okay, Good. So this is how or elimination works in general. And what we'll do, again, the best way to learn these rules, it's of course good to look at the statement of the rules. In the book, you'll see a very clear statement of the rule. However, you're gonna internalize the rule most by using it. And then, of course, if you have questions about how to use it, get feedback from your preceptor. But I'll just go in the rest of this session, I'll just go through a few more examples and I'll talk as I go through the proof to help you see what I'm doing here. Okay, so the next example here is, so as you would expect, as we go on here, we hope to prove more and more things that we expect to be the case. So again, my goal presenting you with the rules of logic that I have is I would like for you to be able to reproduce the kinds of arguments your intuitions tell you are valid and not reproduce the ones your intuitions tell you are not valid. Okay, so something your intuitions surely tell you is valid is or is commutative, right? So P or Q is really equivalent to Q or P. Again, though, we're not just going to say you can flip those because we want to be very precise about what rules are permitted. And so the only rules that are permitted for or are introduction, which is very liberal. You can introduce anything. You can disjoin a sentence with anything. Or elimination is much more conservative. You have to derive the same thing from both disjuncts and then go through this big complicated process. So now we're going to derive Q or P from P or Q. Okay, so here we are with the assumption P or Q. Okay, now to get your head into thinking this way, think again, if somebody were really logically resistant, that is, they are going to ask you to justify everything you say. So the person agrees with you that P or Q. Now you want to convince them that Q or P. And what you'll do is you argue by cases. So given that you have P or Q, you say, well, what if P were true? Okay, so what if P were true? Suppose P. So that's an assumption. Now, this is where it's a little bit not intuitive because, again, in normal arguments, there's almost never a case to go from P downhill down to something weak like Q or P. But in this case, there is, because you want to show that Q or P follows in either case. So Q or P follows from 2 by or introduction. Okay, now same thing with, now we're going to go to the right-hand side, the second case, so assume P. Same thing, Q or, I did the wrong thing, sorry, let me back up and erase. Assume Q is the right-hand side. So I'm back to looking at line 1 as the disjunction I'm arguing from. Okay, so now again, I do Q or P. So that is also or elimination now from 4. Okay, so now I've done my 2 subproofs. I've argued from P to Q or P. I've argued from Q to Q or P. Q or P follows in either case. So now I can do or elimination. So Q or P follows from the original disjunction 1. The first subproof goes 2 to 3. Second subproof goes 4 to 5. That's or elimination. Okay, and now tabulate dependency numbers. So I carry down the dependencies of the original disjunction. That's 1. Now, the next thing I would do is I would copy down the dependencies of the first instance of the conclusion here. I would copy those down, and then the second instance of the conclusion here, but I get to delete the assumption in both cases. So here, the only dependency that's used to get 3 is 2, so I get to delete that. I get to delete 2 because 2 is the assumption that starts the subproof. In the case here, 4 is the assumption that starts the subproof that leads to Q or P, so I get to delete 4. 4 was a hypothesis that gets deleted when I move to that final or elimination. So there I have it on line 6. I did or elimination. Q or P follows from 1, that is P or Q. So that's a finished proof. Okay, this next case is, again, really, really trivial, but it really makes sure you understand how the rule works. Okay, so we're going to show that P follows from P or P. Okay, so start get back to my original color. So back to black. So assume P or P. Now this is going to actually look a little bit wild. So you may have to rewind this one, pause it, and scratch your head a little bit. Okay, so what do we want to do? We have P or P. We want to argue that P follows in either case. Okay, so what you could say, I'm gonna assume P, I'm gonna conclude P, I'm gonna assume P again, I'm gonna conclude P. But the truth is actually nothing in the OR elimination rule tells you that once you use the first subproof, you can't reuse it. So the fact is, the same scratches on paper can count as both subproofs. Okay, so here's what I mean is if I write now P as an assumption, I can consider this one line, line 2 here, is the first subproof. It's both the assumption and the conclusion of the first subproof, and it's both the assumption and the conclusion of the second subproof. So that means this line 2 is playing the role of possibly four separate things in a standard OR elimination. But that's fine. It's allowed to do that. There's no restriction on reusing a line. Okay, so actually now P follows from, this is where it's going to look weird, 1, 2, 2, 2, 2, because 2 and 2, the first 2, 2 indicates first subproof, starts at 2, ends at 2. The second 2, 2 indicates second subproof, starts at 2, ends at 2. 1 is the disjunction, so that's OR elimination. Then I tabulate the dependencies. I copy down the dependencies of the disjunction, so that's 1. Then I copy down the dependencies of at the end of the first subproof, deleting the assumption number, that was 2. So I get to throw everything away. Same thing with the second subproof. So then line 3 depends just on 1, which is the original disjunction. So that's a complete proof. So line 3 says P follows from P or P. Okay. So this next one, the use of OR elimination in this next problem is not complicated. What's complicated is remembering when you've proved something already and reusing something you've already proved. Okay, so I'll go ahead and start this and explain what I mean. So assume not P or Q, we want to prove if P then Q. Now, we will have an argument by cases. So let me help you attack this from two directions. So again, if you're going from the end back, so you're looking at what you want to prove here, you want to prove if P then Q, you might think the thing I should do on line 2 is assume P. And in many cases, that will be the correct move. In many cases, when you want to prove a conditional, you would just assume the antecedent and then proceed. However, as you start to do more and more practice, you'll start to realize sometimes, on some rare occasions, that strategy is not, it still may work, but it's not fully optimal. There may be a more clever strategy. Now, the reason in this particular case, I'm aware there's a more clever strategy is because I have it firmly in my mind what we proved when we were doing conditional proof. So I remember that when we did conditional proof, we proved two funny little results called negative paradox and positive paradox. So negative paradox says, if you have not P, then you can derive if you have not P, you can derive P arrow Q for any Q whatsoever. So I'll just write that down on the far right side here so you can remember that. So negative paradox says this, not P, you can derive if P then Q. So we already did that. We also derived positive paradox, which says, for example, if you have Q, then you can derive if P then Q. Now, looking back at my disjunction, I have two cases. Either not P is the case or Q is the case. But now, if not P is the case, by negative paradox, if P then Q. If Q is the case, then by positive paradox, if P then Q. Aha, so that's a strategy I can use to finish this proof. It's going to take a little work because now we're going to have to plug in both of those proofs we did before, negative paradox and positive paradox. Okay, so starting with not P, the assumption. So this was an assumption on line 1. Now line 2, not P, assumption. Now I'm just going to carry through my argument that would lead to this result that leads to this result negative paradox. And if you remember, there's one way you can do it is you can do positive paradox, so to speak, and then do contraposition. So I'll just do that again. So I'm going to assume not Q. Then I'm going to write not P arrow not Q. So that's just 2, 3 conditional proof. Oops, sorry, this was a mistake here. Not a mistake. What I wrote was correct, but it won't be useful for me. So let me actually retrace my steps here. So what I want to do is I want to get if P then Q. That's contrapositive, the same as not Q arrow not P. So what I want to do here is not Q arrow not P. That's 3, 2 conditional proof. Depends just on 2. Okay. Now I'm going to do the contrapositive maneuver. So I'm going to assume now P so that gives me not P. And so not Q from 6-4 modus tollens. Okay, so then I finally have Q follows from 2 and 5. And so P arrow Q, that's 5, 8 conditional proof, follows just from line 2. So that whole thing from line 2 up to line 9 was actually just reproducing the argument for the negative paradox result. You know, if I had had my, if I had had an electronic copy of my proof from before, I could have just copied it over into this document, just changing the numbers appropriately, and it would have been correct. Okay, so now, oops, we're up to line 10, so let me get this correct. Okay, so now we're just going to do the positive paradox side. So that's the first subproof. 2 to 9 is the first subproof. I got P arrow Q from not P. Now I get assume Q. That's going to be the second assumption, the assumption of the second disjunct. So that's an assumption 10. So now I just assume P again. Truth is, you know, I could assume P now and then do conditional proof and say if P then Q, but actually I'm just going to borrow the P I already used in line 5, the assumption I made there, because it's to write down assumption of P on line 11, you know, it doesn't really add anything. So I'm just going to write if P then Q. So I can write 5, 10 conditional proof. Again, that just depends on 10 though. Okay, so what we have here now, this up through line 11 is our second subproof. So now finally, I can write if P then Q from line 1, 2 through 9, 10, 11. Or elimination. Then looking back at the dependencies, I would take the dependencies from the original disjunction. So that gives me 1. Then I would take the dependencies from the first instance of the conclusion, that's this, but I get to delete the assumption from this subproof, which in this case was 2. So I get to erase 2. That's the only one that's there. And the same with this one, I would take these numbers and copy them down, but I get to delete 10 because 10 was the assumption that subproof began with. So now finally on line 12, we're finished here. But as I said before, if you'd remembered very clearly negative paradox and positive paradox, this is actually nothing really new other than the one application of OR elimination we did at the very end. Okay. Now, another nice thing that OR elimination lets you do is OR elimination lets you see how OR interacts with AND. In particular, you have very familiar distribution laws that where OR distributes over AND vice versa. So in this case, we're going to show that P or Q and R follows from the conjunction P or Q and P or R. Let me get back to my original color. P or Q and P or R is my assumption to begin with. Okay, so now in truth, it's going to be easier conceptually if I just take apart one. So it's the conjunction, so I'm going to take it apart into two. It's two conjuncts, so one and elimination, P or R, one and elimination. Okay, so I've just broken that conjunction on line one into its two parts. Okay, now this is a little bit complicated what's going to happen next, but if you think a bit geometrically, it's not too bad. So what we've got now is two disjunctions, P or Q and also P or R. So this is kind of weird because you know basically that one of, you can combine, there's four total possibilities, right? So to speak, is, P, you could have from the first disjunct, P or Q disjunction, you could have P could be true. From the second disjunction, P could be true, but also R could be true. So you could have P and then P again and R, or you could have P and R, and so on and so forth. So in essence, it's a big argument by cases, four different cases. But actually, it turns out to be a little bit simpler than that, because if we start working with the first disjunction, so we start with the P or Q, and we say, let's assume from the first disjunction, P. Notice actually that by itself, line 4, is sufficient to get the conclusion, right? The conclusion we want is P or Q and R. So once you have P, the conclusion follows. Okay, so if we assume the first disjunct of the first disjunction, P or Q, then the conclusion follows. Okay, so P or Q and R. So that's just, oops, that should be an assumption on line 4. And then line 5 is for or introduction. Okay, so that deals with anything where P is true in the first case, the conclusion is true. So we only need now to look at where Q is true in the first disjunction. So suppose now Q, that's again an assumption. Okay, now the conclusion doesn't, of course, follow from just Q. You can't get P or Q and R from just Q, because obviously P doesn't follow from just Q, and nor does Q and R. So we now need to go and draw upon the second disjunction. So we're going to now look at 3, we're going to use it. So we're going to look at both sides of the second disjunction, which is P or R. But now if we assume P from the second disjunction, so if we assume P again, and technically I didn't need to do that because I had assumed P before and I could just reuse it. But the thing is, if I multi-thread my cases too much, I will get confused. So I'm just going to actually forget that I already dealt with that other case. Okay, so I'm going to make a new assumption of P, and I'm going to realize again that the conclusion follows. So P or Q and R follows from line 7 or introduction. Okay, and now finally, if I assume R from the second disjunction, so I assume R, now lines 6 and 9 together give me Q and R. And so that, of course, does give me the conclusion I want. That gives me P or Q and R. So now 10 or introduction. Okay. So now basically I've argued to the end of all the individual cases. The last thing I need to do is to get rid of all the suppositions I made and realize that this just follows from the original disjunctions, the disjunctions on line 2 and 3. Okay, so looking at line 11 in particular, line 11, we got from 6 and 9. Okay, 9 is supposition from the second case of disjunction, or the second disjunction, right? So in other words, we can now, if we look at lines, I'll use some color to keep this clear. So if we look at lines 11 and 8, these can be considered to be deriving the same conclusion from the disjuncts that occur in the second disjunction. So the disjunction on line 3, that is the disjunction of P and R. Okay, so then what I can do is I'm going to, on line 12, basically get rid of those two little subproofs. Okay, so I'm going to write P or Q and R follows now from 3, as I said, 7, 8, 9, 11, or elimination. Okay, now the tricky thing is tabulating dependencies. Here on, okay, so here on 7, 8, there's going to be no new dependencies taken down, because the only dependency that appears in line 8, the first that conclusion, is the assumption 7. In the case of this 11, the assumption was 9. So in line 11, the assumption that led to that conclusion was line 9. We gathered, though, we picked up another dependency along the way, 6. So the final thing here is going to be 1, because 1 is the dependency of the disjunction on line 3, and then 6. Okay. Now, we're basically now at this stage going to treat line 12 as derived from the first disjunction, that is what's on line 2. So now I'm going to say this follows from P or Q and R, line 2. Then the first subproof was 4 to 5. Second subproof was 6 all the way down to 12, or elimination. Okay, now the big tabulation of the dependency numbers. We take the dependencies of the disjunction on line 2, so that's 1. We take the dependencies of the conclusion in line 5, but we get to take away the assumption number, which was 4, so that's nothing. So we take the 4 here in line 5, and we take away the 4. And then finally, we look at line 12, and we get to take away the assumption, which was line 6. So the dependencies of 12 are just 1 and 6, so we just get another dependency on 1, and that's fine because we already have that. So 13, finally, P or, and then in parentheses, Q and R depends on just line 1. So it's a complete proof now. Complicated, like I said, this is bookkeeping, complicated bookkeeping. The truth is, even if you find yourself quite confused, there's two sides to keep yourself sane here. There's, on the one hand, using your intuition about what you're doing. So in this case, remembering that really what you're doing, this complicated linear proof, is you're arguing by cases where you have two disjunctions. So you're arguing case by case. The second way to keep yourself straight is just remember these rules that we have, they're syntactically totally precise. So you can always go back line by line and read the line and make sure absolutely you followed the rule, the letter of the law, and you won't make any mistakes that way. Okay, so that's the last one we'll do for today. As I said, disjunction elimination, the concept is fairly clear. It's argument by cases. Disjunction elimination is argument by cases. As we've just seen here in this last instance, the actual tabulation of dependencies can be quite complicated. And so it's good to start out with easier ones. And although they may seem trivially easy, be very careful and then work up to the more difficult ones. In the next session, we'll cover our last rule of inference for propositional logic, and that is reductio ad absurdum.